Let's do an example from the homework to illustrate a hypothesis test for the population proportion. You are conducting a study to see if the accuracy rate for fingerprint identification is significantly more than 0.65. You're going to use a significance level of 1%. Okay, they've got the hypothesis, the null, and the alternative already stated for us. Remember, the null hypothesis, here they're writing the letter P because we're talking about the accuracy rate, which would be the proportion of successful identifications, which is out of the total number of trials. I mean, they want to know if the accuracy rate is more than 0.65. So that is a greater than symbol right there, which is a right tail test. And they give us some sample statistics here. The sample size is 290. And there are 193 successes. And a proportion is the number of successes out of the sample size, right? Furthermore, when we calculate our test statistic, this P with a 0, that is the hypothesized value, that baseline. So that is the 0.65 showing up right here or right here. Let's get a decimal approximation for our sample proportion. Sometimes that's pretty nice. So this is about 0.66551724. Now I'm holding on to a lot of decimals so I don't make too much of a rounding error. Okay, we've got all of our components here. Let's compute our test statistic. We're going to plug it all in. Our test statistic, the P with a hat, the sample proportion, about 0.66551724. We're seeing how different that sample proportion is from this baseline proportion. And that's with respect to the standard deviation. So that's 0.65 times 1 minus 0.65 over the sample size of 290. That's all on the square root. Okay, let's compute this. I like to do the numerator first and the denominator second. So I'm going to take our 193 divided by 290 and subtract the 0.65 to get our numerator there. And now I'm going to calculate the denominator. Square root 0.65 times 1 minus 0.65. Close parentheses, divided by 290. But now I need to close the parentheses for the square root. Okie dokie. Okay. Usually that denominator is a small number, so that is satisfying to me. I'm going to rewrite these numbers. Now I'm going to do the division here in my calculator to get our test statistic. So this is approximately 0.55. We always want to round those to the second decimal place because we're going to take this to our z table, and the z table only has 2 decimals worth of accuracy or precision, so 0.55. That's not a very big test statistic, right? Because if you think about this as a standard deviation, being 1 standard deviation from the mean is not that far away. And this is about half a standard deviation away. So I'm expecting a p-value that's kind of large here. I like to draw a picture, and I highly recommend that you always draw a picture too, because what we're about to do is find an area in the z distribution. 0 is always in the middle. Our test statistic was 0.55. 0.55. We want the area to the right of this test statistic. And it's to the right because this was a right-tailed test. If this was a left-tailed test, I would be shading the other direction. So this is our p-value, and that's what we want to go find in the z-table. So I'm going to pop open my z-table. Okay, here it is. Remember how the z-table works. If you look up a z-score, then the area inside the table here is the area to the left of that z-score. We want area to the right, so we're going to end up doing a 1 minus. But the z-score, the test statistic that we are looking up, is positive 0.55. So cruising down here to 0.5 is that row, and I need to go to the column that says 0.05. Right, that is 0.55. So this area that I need for our work here is 0.7088. 0.7088. And hopefully the picture has guided us, right? Because our answer cannot be 0.7088. Look at the picture, right? This is 1 minus 0.7088, which is 0.2912. So that is our p-value. I will circle it in yellow. What we are going to do is, in the next step, is state our conclusion. Our conclusion is from comparing the p-value to alpha. Get out of here, calculator. Alpha is our threshold for what's considered significantly different, or significantly larger, or smaller. 0.01. So is our p-value bigger or smaller than 0.01? Well, it's 0.2. So our p-value is bigger or greater than alpha. So our conclusion will be to not reject the null hypothesis, aka we are going to fail to reject the null hypothesis. That's how the homework has it stated. What does this mean about the accuracy rate for fingerprint identification? Because we are not rejecting the null hypothesis, that implies that there is not sufficient evidence for the alternative. Now, when we say the alternative, that's still kind of technical. So I'm going to say that there is not evidence for, I need to translate these symbols. There's not evidence for the fingerprint accuracy, fingerprint identification accuracy being larger than 0.65. Because we are not rejecting the null hypothesis, we do not have evidence for the alternative. The alternative says that the accuracy rate is larger than 0.65. Now let's go type in all of our answers here and see how we did. They're trying to trick you right here. We never accept the null, we just cannot reject it. So careful there. You're never going to click the acceptance button. Now they have this translated here, and we're going to need to think about which one of these conclusions is consistent with what we just wrote down here. There is evidence to warrant the rejection. No, we're not rejecting. This one says there is not evidence to warrant the rejection that the accuracy rate is more than 0.65. We are not rejecting. That's not quite right either. The one that's correct is there is not evidence to support the claim that the accuracy rate is more than 0.65. This one, the second one, almost has a double negative. There's not evidence to reject this. So that one's a little tricky. Let's see how we did. Green check marks, very satisfying.